Alright, what's up, Algebra 2 Trig? Today, we got another lesson. It's called 9.3 Geometric Sequences, and the EQ is how do I find the terms of geometric sequences? Alright, Mr. Don, take it away. I'm out later! What's up, baby?
Okay, thank you, Jimmy. So we're going to go ahead and start first off by writing down this definition. So please copy that down. The definition of a geometric sequence. And it's actually a little bit different from an arithmetic sequence because a geometric sequence is based on the idea that we have a common ratio. In other words, something that we're multiplying or dividing between two numbers. Okay, in this case, it has to be consecutive numbers. And we're going to go ahead and look at this one. So example 1, determine if the sequence is geometric. So here I'm going to list out a couple of numbers, 2, 4, 8, 16. And dot, dot, dot. In other words, a sequence is going on. So to determine if something is geometric, we want to check between each set of consecutive numbers, what is the ratio that we are multiplying or dividing by. To do this, we're going to find R. And in this case, I'm going to do 4 divided by 2. So my ratio for the first two is 2. And I'm going to double check just to make sure. 8 divided by 4. That's also going to be 2. So it turns out, as I go along, it's going to be a ratio of 2 every single time. So yes, this is a geometric series. And then continuing on with example 1, so let's call this example A, and then the next one B. So the next one I'm going to have 1, 4, 9, 16, 25, dot, dot, dot. Now, just looking at this, I can tell already that the ratio isn't going to be the same, even though I can find some sort of pattern. So here I have a ratio of 4, and then the next one, 9/4. So that's definitely not going to be the same thing as 4. So I know immediately that this is not going to be a geometric sequence just because the ratios are not the same. So make sure you're understanding that there's a difference between this guy and this guy. Okay, so they're not actually going to be the same because we're talking about a common ratio to the nth power versus this one being n to the second power, or every number like number 1, 2, 3, so on and so forth being squared. Okay, so this is what we're focusing on, not that. Okay, so that's example 1, just to tell if something is geometric. So we're going to move into example 2, where you guys have to give us the first few terms of a geometric sequence. So we're going to write first 5 terms of the geometric sequence. Okay, and then in this case, it's going to be if the initial term, A1, is equal to 5, and the ratio is 2. So in this case, we're going to give it 2. And in order to calculate this, we actually need to use another formula. So go ahead and copy this one down. So we have the nth term of a geometric sequence has the form A sub n equals initial value A1 times the ratio to the n minus 1 power. Okay, the n minus 1 is the key thing right there, so make sure to copy down that part correctly. And we're going to go ahead and write the first 5 terms. So easy enough, we have A1 is equal to 5 because that's already given. If you wanted to show work though, this is the same thing as 5, the initial value A1. Let's go ahead and write that. A1 times r to the n minus 1 times 2 to the 1 minus 1, because n in this case was 1. So we have 5 times 2 to the 0, and that's going to be 5. Then we just go ahead and go on, fill in the rest, A2, A3, A4, and A5. So we get 5 times 2 to the 2 minus 1. That's going to be 5 times 2. That's going to be 10. Now for those of you who don't want to plug in constantly and have to deal with pretty large exponents, You should notice that the ratio is 2, which means that each subsequent number is just going to be multiplied by 2. So A3 will be 20, A4, 40, and then A5, 80. So you have your first 5 terms, 5, 10, 20, 40, and 80. Okay? So moving on from that, we're going to go ahead, do a lot today. Example 3. And instead of listing all the terms, we're going to find a specific term. So we're going to find the nth term. For this problem, we're going to be given the initial value, A1. And A1 is going to be equal to 3. Our ratio is going to be 1/3. And n will equal 5. Okay? So in this case, I'm looking for the 5th term of the sequence. So I'm going to use that formula I had over here. And I'm going to use a sub 5 is equal to a sub 1 times r to the 5 minus 1, because I substituted in 5 for my n. Then I'm going to go ahead and plug in these other two values. So a5 is equal to 3 times 1/3 to the 4th power. 1/3 to the 4th power, once you distribute that exponent in, you're going to have a5 is equal to 3 times 1/81. We're going to leave that as a fraction to make it easier on us. So a5 is equal to 3/81, or simplified as 1/27. Okay, so that's going to be the 5th term in this geometric sequence. And as you can see, this ratio is actually a fraction, and you will be seeing that in your examples tomorrow as well. Okay, moving right along, we're going to go ahead and go to the 4th example, where we don't give you A1, R, or N, but you guys have to figure out on your own. Okay, so switching forward. So here, example 4. Again, we're going to find the nth term. And this time we give you a sequence, so 2, 10, 50, 250, and 1250. And then dot, 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 because the sequence goes on. And we're looking for the nth term, or 10th term actually. So n equals 10. So in this problem, what I need to do first is actually to find the ratio. Looking from here to here, I have 10 over 2. And that's going to be 5. And I'm going to double check. 10 to 50, okay, I'm multiplying by 5. 50 to 250, multiplying by 5, so it checks out. My ratio is definitely 5. Now that I have my ratio, I have my n value. I'm going to use that formula again, and let's go ahead and write it up here. So an is equal to a1 times r to the n minus 1. So a sub 10 is equal to, initial value is 2. My ratio is 5. And we're going to do 10 minus 1. So we have 2 times 5 to the 9th power. Now in this case, we're definitely not going to expect you to multiply all of that out. So if I were to plug that into my calculator, I actually get 2 times 390,625. Distributing the 2, I end up with 781,250. And that's going to be my 10th term for this really, really big sequence. And that helps us a lot in terms of reducing all those calculations and having to list out all the numbers. And we've got one final example, so go ahead, push this on up, where we combine a lot of what we just did. And basically what's going to happen is that they're going to give us 2 random numbers. So in this one, the 3rd term of a geometric sequence is 16. And the 6th term is 1024. And based on that, they're going to ask us to find the 10th term. Now, the difficulty I have here is that I can't find r by dividing 1024 and 16. Because if I were to do that, that would give me an r value that's actually not the r value for this problem. The reason is because the third term and the sixth term are obviously not consecutive with one another, so that would not be what we do. Instead, I'm going to have to use, again, that formula. But just like before, we manipulated it a little bit, where we replaced the n and the 1 with the values that were actually given. So in this case, I'm going to substitute n with 6, and I'm going to change out the 1 right here and right here with 3 instead. So a sub 6 is going to be equal to a sub 3 times r to the n, which is going to be 6, minus 3. Again, I substituted n with my 6 because I'm given a 6th term. Then I replaced the 1s with the third term, so I'm replacing them with 3. Okay? So now I get to substitute these numbers in. So the 6th term is 1024. The third term was 16. R stays the same because that's what I'm looking for, and it's r to the third. So some algebra 1 here. We're going to divide both sides. I get 64 is equal to r to the third. I take the cube root of both sides. So I find out that 4 is my ratio. I'm going to use that ratio and use all of these formulas once again in order to find that 10th term. So now I'm going to find a sub 10. And because I don't have my initial value, you guys could calculate it by using that ratio, or you can use the third term. Personally, because I'm given the third term, I might as well find out what my second and first are. Okay, so if my third term is 16 and the ratio is 4, it makes sense that my second term is 4 and my first term is 1. So this could be used as my a sub 1, where I just plug it in directly into this formula. However, let's say that you're not given a third term and you're given like the 15th term. Backtracking all the way to the initial term actually takes a lot more work, so you can actually just use what they already give you. So I'm going to use a sub 3, and I'm going to use my r value as well. So first let's just write r. And then the exponents, once again, are going to mimic exactly what we see. So instead of n, I use 10, minus, instead of 1, I'm going to use 3. So a10 is what we're looking for. A3 is what we're given, so that's 16. We're given our ratio of 4, and then 10 minus 3 is 7. So 4 to the 7th power, once again, is such a huge number. Not something I want to deal with on my own, so calculator gives me 16,384. Multiplying that all out, I get my final answer that the 10th term in this geometric sequence is 262,144. All right, so that covers 5 examples as part of 9.3 geometric sequences. Hopefully you're able to follow along through all of this. It's very similar with each example, just kind of increasing the amount of steps with each one. So if you need to, rewatch, replay as needed. Otherwise, move on to the Google Forms, and we'll see you guys tomorrow.
What's up, baby?